In pursuit of sharing technical knowledge and to support new engineering entrants, I, Pranav, will be presenting today's presentation on Power Transformer Part 83. As the topic is of the continuation, so for your convenience, the link of the previous one is given under the description box. Let's start with transformer oil acidity and polarization loss. Transformer oil acidity and polarization loss, that is dielectric loss or tan delta, are closely interrelated because they both are the resultant effect of chemical degradation of insulating oil. Increased acidity caused by oxidation leads to the formation of sludge, organic acids, and polar compounds as major contaminants that raise the oil's conductivity and dielectric loss factor, ultimately decreasing the insulation strength of the transformer. Acidity in transformer oil is a key indicator of chemical degradation due to oxidation and hydrolysis. Oxidative reactions can produce acids, aldehydes, and ketones. Hydrolysis in transformer oil is the chemical breakdown of solid cellulose insulation, that is kraft paper, caused by moisture and acidic byproducts. At elevated temperatures, hydrolysis is in transformer oil becomes more pronounced, leading to formation of additional polar spaces. Along with oxidation byproducts, these polar molecules increase the oil's overall polarization response. The concurrent accumulation of carboxylic acids and moisture further raises the concentration of ionic impurities, resulting in higher electrical conductivity and greater dielectric power dissipation. Collectively, these processes cause an increase in the oil's complex relative permittivity, particularly the dielectric dissipation factor, thereby indicating a deterioration of its electrical insulation properties. Consequently, higher acidity in transformer oil generally correlates with increased complex permittivity and dielectric loss, or both are driven by the buildup of polar degradation products formed through oxidation and hydrolysis. Thermal degradation and oxidation promote the generation and retention of moisture in paper insulation, which in turn accelerates further degradation, creating a self-reinforcing failure mechanism. In an oil paper insulation system, polarization loss that has to arise as because the dielectric cannot respond instantaneously to a changing electric field, that is oscillating electric field, leading to a delay between the applied alternating voltage and the resulting polarization current. Polarization loss is primarily influenced by two key dielectric phenomena that occur under an applied electric field, especially in the low to medium frequency range. One, interfacial polarization. Number two, dipole polarization. These two phenomena involve in reorganization of ionic changes and orientation of polar molecules, which require overcoming internal viscous resistance, converting electrical energy into heat. Now, interfacial polarization. Interfacial polarization arises due to the accumulation of charge carriers at the boundary between the insulating paper and the transformer oil, with having different permittivity and conductivity. When an alternating electric field is applied, mobile charge carriers, that is ions, start to migrate and accumulate at these interfaces. But the redistribution of this charge does not occur instantly because it has to overcome a viscous resistance in the oil, and number two, structural resistance in the paper. Because ionic charges require a finite time to migrate and accumulate at interfaces, interfacial polarization becomes more pronounced at low frequencies. Most important. The delayed response leads to a significant phase lag between the applied electric field and the polarization, resulting in increased energy loss. Number two, dipole polarization. Dipole polarization involves the orientation of polar molecules, that is dipoles, within the insulation material, such as water molecules, moisture, and degradation products like acids, alcohols, etc. When subjected to an alternating electric field, these dipoles attempt to align with the field, but their motion is opposed by internal friction. The frictional loss causes energy dissipation known as polarization loss. In the low to medium frequency range, the dipoles cannot reorient quickly enough with each field reversal, resulting in a phase lag between the applied field and polarization, which leads to energy loss in the form of heat. Conclusion. The interfacial polarization and dipole polarization in an oil paper insulation system have a strong dependence on the amount of moisture or water molecules present. Water molecules significantly alter the dielectric properties of the insulation by increasing ionic conductivity and introducing additional polar dipoles. As a result, both charge accumulation of interfaces and dipole orientation effects, these two, both charge accumulation at interfaces and dipole orientation effects are enhanced, leading to higher polarization losses. Leading to higher polarization losses. Polarization losses, a major component of dielectric loss, occur throughout the entire volume of an insulating material when it is subjected to an alternating electromagnetic field. This is because The process involves the continuous orientation and relaxation of atomic, molecular, and interfacial dipoles across the whole bulk of the dielectric, including both solid, as for example, kraft paper, and liquid insulation, that is oil. Hence, the polarization losses in insulation systems are thus to compose with the underneath aspects. A. Continuous reorientation of dipoles. Atomic, molecular, or interfacial dipoles, such as polar functional groups in solid insulation like paper, or polar molecules in liquid insulation, continuously attempt to align with the alternating electric field. Because the field is constantly changing direction, this alignment is also continuously changing. B. Relaxation, that is lagging response, phase lagging rather, and energy dissipation. The dipoles cannot follow the applied field instantaneously due to inertia and internal friction. When field reverses direction or its intensity is reduced, the dipoles relax back toward a more random, that is disordered condition, disordered state under thermal agitation. The time lag phase in polarization and depolarization processes causes energy dissipation in the form of heat, which is referred as the polarization loss. C. Transformer no load losses. Apart from no load losses, even in a healthy transformer is sometimes referred to polarization losses. Most important, a part of no load losses even in a healthy transformer is sometimes referred to polarization losses. Transformer no load loss, often called coal loss or iron loss, is the power loss in a transformer while excited at rated voltage and frequency, but not supplying load. So, it represents the power dissipated in the magnetic core whenever the transformer is energized, regardless of the load connected to the secondary side. No load losses are caused by the alternating magnetic field in the core, resulting from hysteresis, that is magnetic resistance, and eddy currents. These losses are generally independent of the load magnitude. The no load loss magnitude is dependent on the applied voltage and frequency of the power supply. However, as the core flux remains relatively constant at rated voltage and frequency, no load loss is considered a fixed loss. No load loss tends to change slightly with temperature of the core. No load loss of a transformer is primarily caused by losses to the core steel, and its magnitude is thereby to differ as corresponds to quality of the silicon steel sheets used in the core. No load loss is a power loss and often represents a cost to the user during the lifetime of the transformer. Maximum value of the no load loss of a transformer is specified and often guaranteed by the manufacturers. Mechanism of dielectric loss as relates to polarization lag, that is dielectric relaxation. Ionization loss and polarization loss are two primary components of dielectric loss in transformer oil paper insulation system. However, they differ significantly in their physical mechanisms, underlying causes, and their impact on the condition and diagnostics of the insulation system. Polarization loss in transformer insulation is a critical dielectric phenomenon where energy is dissipated as heat due to delayed response of molecular dipoles, charge carriers, and interfacial charge accumulation under an alternating electric field. Polarization loss is a key contributor to the total dielectric loss in a material, and the loss is at its maximum when the dipole relaxation time matches the inverse of the angular frequency of the applied alternating field, that is 1 by omega, or when tau, that is relaxation time, equals to 1 by omega, that is omega tau equals to 1. Transformer polarization losses are strongly influenced by temperature and frequency. These losses reach their maximum at low frequencies and elevated temperatures, primarily as a result of intensified interfacial polarization and increased electrical conduction mechanism within the insulating material. Polarization losses, specifically those due to dipolar, that is orientation polarization, are generally dominant in the low frequency range. At low frequencies, permanent electric dipoles have sufficient time to align with the oscillating external electric field. This continuous rotation and reorientation of dipoles create create frictional losses, that is dielectric losses, as the dipoles attempt to follow the applied field. With increasing frequency, polarization mechanisms such as dipolar, interfacial, and ionic polarization cannot depend quickly enough to the alternating field. As a result, the contributions of these polarization mechanisms are going to diminish, thereby leading to a reduction in dielectric or polarization losses. Elevated temperature primarily reduces the viscosity of the oil and weakens the cellulose molecular structure, which in turn decreases the dipole orientation time and increases the mobility of charge carriers. This enhanced charge carrier mobility leads to higher ionic conductivity and higher dielectric polarization loss. The trend of polarization loss in a transformer is generally characterized as a major component of dielectric loss, exhibiting the following behavior. A, the dielectric loss factor, that is tan delta, decreases exponentially as frequency increases. Important. The dielectric loss factor, tan delta, decreases exponentially as frequency increases. B, the phenomenon is primarily because of the limited response of polarization mechanism. The phenomenon is primarily because of the limited response of polarization mechanisms. C, in contrast, increasing temperature leads to higher polarization losses as it reduces the relaxation time of polar spaces. D. This enables them to establish their polarization state more quickly, thereby decreasing the time constant while increasing the overall magnitude of dielectric loss. Significance of dielectric loss in relation to polarization losses. In an alternating electric field, dielectric performance is strongly influenced by polarization phenomena. Polarization losses represent the energy dissipated due to dipole reorientation within the dielectric material and charge accumulation at the interface in composite dielectrics, whose permittivity is not the same. The overall dielectric loss mechanism is a combined effect of conductivity loss due to leakage current through insulations and number two, polarization or relaxation loss. Relaxation of dipoles rather. Polarization or relaxation loss that has to occur due to the process by which polarization lags behind the applied voltage. This phase lag causes part of the electrical energy to be converted into heat during each cycle. Hence, dielectric losses are primarily caused by polarization lag and leakage current, that is, conduction current in insulating materials under an alternating electric field, resulting in energy dissipation as heat. Dielectric losses are not inherent static properties of a material. Rather, they are dynamic in nature and depend on several interrelated parameters such as one, frequency of the applied electric field, temperature of the environment rather, moisture content and contamination, molecular structure and type of material, materials relative permittivity or dielectric constant, voltage stress or electric field intensity. Last one, insulation condition, that is aging criteria. Dielectric loss is indeed strongly dependent on the frequency of an applied alternating electric field. Mechanism of dielectric loss and polarization lag. Dielectric loss arises in an insulating material when the dipole polarization cannot respond instantaneously to an applied alternating electric field. As a result, the polarization lags behind the applied electric field, leading to energy dissipation. During the polarization process, particularly in dielectric materials, dipoles experience resistance to reorientation primarily due to a thermal agitation that tends to randomize dipoles alignment, and B, the rotation and rearrangement of dipoles require overcoming the intermolecular forces and molecular viscosity of the medium. The effect of thermal agitation plays a crucial role in dielectric polarization, acting as the primary opposing force to the alignment of dipoles in a dielectric material under an external electric field. that is thermal agitation, most important. Thermal agitation or thermal motion in solid insulation such as scrap paper used in transformers refers to the random vibrational motion of atoms and molecules caused by heat energy. If the absence of an electric field, thermal energy keeps polar molecules such as those in cellulose randomly oriented, resulting in zero net dipole moment. When an external electric field is applied, it tends to align these dipoles. However, thermal agitation continuously disrupts this alignment. The net polarization of the material is therefore determined by the balance between the aligning effect of the electric field and the randomizing effect of thermal motion. As temperature increases, thermal agitation becomes more intense, increasing the kinetic energy of the molecules. The increased kinetic energy makes it more difficult for the electric field to maintain dipole alignment, generally reducing the overall polarization. Consequently, higher temperatures can also lead to a decrease in dielectric strength and insulation resistance. Consequently, higher temperatures can also lead to a decrease in dielectric strength and insulation resistance. When an external electric field is removed, the aligned dipoles gradually return to a random orientation due to thermal agitation and internal intermolecular forces. This process is known as relaxation, and the time required is called the relaxation time or dipole relaxation time. In solid dielectrics, molecules or dipoles are not completely free to move. They are constrained within a fixed structure. Mainly in solid dielectrics, molecules or dipoles are not completely free to move, like liquid insulations, that is oil. They are constrained within a fixed structure, fixed molecular structure rather. As a result, this orientation requires comparatively higher energy than in liquid or gases. Although thermal agitation in solids is lower than in liquids and gases due to restricted molecular motion, it is still sufficient to disturb dipole alignment, especially under an oscillating electric field. Because of these constraints, dipolar polarization in solids does not occur instantaneously. Instead, it takes a finite time to develop after the application of an electric field. This is referred to as the relaxation process. The phenomenon of dipole relaxation or dielectric relaxation is characterized as a fundamental concept in understanding how dielectric materials behave under alternating electric fields. Let's stop here, further to be continued at later stage. Thank you for listening the video. Kindly do like, share and subscribe. Your subscriptions would encourage to post more videos. Also share your comments or feedbacks in the dedicated comment section. If you have any suggestions or specific topic you want, then let me know in the comment section, please. Thank you. Thank you for patient hearing.